Hello everyone, welcome to my talk. We're going to be discussing the spectral characterization of 8-phosphorus array Hamiltonians in silicon. But overall, this is going to be discussing analog quantum simulations in silicon phosphorus nanodevices. So what did I just say right here? So analog quantum simulations, very succinctly put, is the implementation of the continuous properties of quantum systems to simulate any sort of like behavior or model that we desire. And in this case, our continuous quantum system that we care about is the tunneling energies and the on-site energy corrections for these silicon and phosphorus nanodevices. And the reason why we care about these devices a lot is because they have been experimentally proven to be promising candidates for simulating something called the Fermi-Hubbard model. So what is the Fermi-Hubbard model? So the Fermi-Hubbard model essentially describes how electrons interact with each other on a lattice of atoms. The main terms to understand is that there is this kinetic energy term that describes the electrons kind of tunneling between atoms or sites. There is the on-site energy. There is the on-site energy that comes from the electrons being at each atom. And additionally, there is the term of that accounts for the Coulomb repulsion of electrons interacting both at their site and neighboring atoms. The problem with the Fermi-Hubbard model, though, is that it gets really analytically complicated to solve as it scales up. And so there's been a lot of research into finding numerical methods to study the Fermi-Hubbard model, and in this case of this talk here, analog quantum simulations for it, because the Fermi-Hubbard model has been shown to exhibit lots of interesting properties that are present in quantum materials. And so in the context of our research here, we are studying this 8-phosphorus model array. Previous research has been done on 2, 3, and 4 sites, but we wanted to scale it up to 8 atoms, and include nearest neighbor and tunneling, face-to-face tunneling, and on-site energy corrections for the corner and the face separately. What makes this system so interesting is that it is the smallest ring type geometry that has 2 types of sites, specifically corner sites and face sites. This site is also interesting because we want to also understand what might be the effect later on if we add a site in the very center, creating a full 3x3 array. So having that comparison is super valuable, especially because for the last point I'll mention here, this ring array has been shown to display lots of really interesting ferromagnetic properties. So if we can simulate this system, we might learn a lot about it. And so how do we analyze this model? So we use spectral analysis via exact diagonalization. And the way this works is that we take a single electron and we start it at some site. Maybe it's either a corner, maybe it's at either a corner or a face, and then we solve the time-dependent Schrodinger equation and to see how this single electron state evolves over time, spreads out throughout the model. And then we want to compare our initial state to this time-evolved state. And what we find is that this overlap exhibits sinusoidal motion governed a lot by the differences in the eigenvalues for our model Hamiltonian. And this is important because these differences will, if we solve them, will give us information about our tunneling energy and also the on-site energy corrections. So after we can plot our probability, we then account for singularities that might occur from taking the difference of either the same eigenvalue or degenerate eigenvalues. So that way, when we're taking the Fourier transform of our plots to search for these frequencies, we don't run into as many issues. So we do all that, but what do we have as a reference? So as a reference to the actual silicon nanodevices, we use type binding calculations, which are an experimentally verified way to replicate the effective masses and the energy bands in our silicon nanodevices. And so if the data we get from our model, after taking the Fourier transform, lines up very well with our type binding data, then we can say something about like what type of model these specific silicon quantum devices can model. Right? And so what did we find? So one of the first things we found is that by setting the face-to-face tunneling energy larger than the nearest neighboring tunneling, which basically means the electron is more likely to tunnel if it's at a face to another face than to a nearest neighbor, we start to see some qualitative similarities, which is really interesting because at least when I was first in analyzing this model, I assumed that an electron would be more likely to tunnel to a site closer to it than one further away from it. So this warrants some interesting research and further study. But we also know that we need to improve our model to account for more elements and features to match what we see in our tight binding data. Because as you can see here, there are a lot more frequency peaks in this corner state than we see in our model state here. And so we can't quantitatively say what these tunneling energies are yet. However, we deduce that what's happening here is that there is hybridization occurring between the ground state of the electron and higher energy states in the electron. So that leads us into further directions when further studying this. We want to incorporate the hybridization between all these. We want to incorporate the hybridization of the energy levels in our model, so that way we can we see more frequency peaks in our model and will more closely line up with our tight binding data. We then want to develop a machine learning protocol to more practically sort through all possible combinations of tunneling energies and on-site energy corrections to match that with our tight binding data, because doing that by hand for every possible separation distance between sites in our devices is impractical. And if all that works well, we then want to extend the analysis to larger systems like our full 3x3 array, and also include more electrons, because in the Fermi-Hubbard model, we're not just looking at the behavior of one electron, we're looking at multiple electrons. So incorporating multiple electrons into our study here will provide interesting research. And so I want to just thank all these people who have helped me out throughout research and just having a great summer. I would not be where I am without them this summer. So thank you very much.